Okay, so let's have a look at the velocity of our simple harmonic oscillator. We've looked in detail at the displacement, and here then we've got, as usual, our oscillator starting from a positive maximum displacement plus A, where A is the amplitude. The dotted line in the middle, of course, is our equilibrium position. And, well, if we visualise that, the motion of this object, it's just arrived, it's on these springs as usual, or whatever it is, and it's just arrived at its maximum positive position. That means it's not moving. In fact, V there is 0. Well, it's useful here to bring in our friendly, helpful circle. So in the auxiliary circle, if we kind of visualise our blob which is moving around that circle, well, at that moment, remember that it goes at constant speed. So, well, can you see that the velocity around the circle, the component in the line of the oscillation is 0. All its velocity is purely perpendicular to the oscillator. And so that's kind of interesting, and we can keep going with that process of thought process by considering a moment later when we might have the oscillator on its way zooming through the equilibrium. So there it is, and now we know now that it's moving to the left, and you can, I won't draw the springs this time, but we know, don't we, that at this point it must be moving with its maximum speed because it's in the middle of its motion. If you imagine a mass on a spring there, it's going to be moving at top speed when it's zooming through the equilibrium. Well, looking at our auxiliary circle, of course, well, that's the moment where all the velocity of the circular motion is in the same direction as the line of the oscillator. And so that's why. So it's V, velocity here is the max it can be when it's going through equilibrium. But of course, one thing just to realise is that it's, of course, at that moment it's negative because it's moving in a negative direction. And so let's keep going. Let's look at the next step, and this time when I think I am going to draw on the springs so that it kind of looks a bit nicer. Well, the next step is when it's reached to its extreme left position. So in other words, its maximum negative displacement over here. Well, it's going to kind of crunch to a halt again, isn't it, there? Because it's being slowing down by the springs, it's its maximum negative displacement. So that position there is minus maximum displacement, minus A. And our blob now is zooming straight down in its anticlockwise motion, still at speed v, because it's always at speed v on the auxiliary circle. But of course, that means that the component of the velocity in the direction of the oscillation is 0 again. So we can sort of see the relationship developing, I think, between the oscillator and the displacement and the velocity. Last one, back in the equilibrium position, zooming the other way. And so let's put on our springs real quick. And so this time it's at maximum full tilt again, it's at its maximum velocity, and our blob on the auxiliary circle is now speeding along to the right, to in the same line of the oscillation. So again, our velocity is a maximum value, but of course this time it's positive maximum, whereas last time it was negative maximum when it was going the other way. Now we can say something a little bit more about our maximum velocity, of course, because it's circular motion. Well, we know that the velocity of something moving in a circle, v, is omega r, if you remember back to circular motion. Well, of course, in the auxiliary circle, r is the displacement. So that means that v equals omega a. Well, that's only equal to the velocity of the oscillator when the oscillator is in equilibrium at its maximum velocity. But that's really powerful, so that means that we know that the maximum velocity of an oscillator is, well, either plus omega a when it's going to the right, or minus omega a when it's going to the left. So that's quite a kind of important thing to realise. So let's see then, finally, what the graphs tell us. So there's our displacement graph, remember. We've released this blob at maximum positive displacement plus A at time equals 0. So of course, it's a cosine graph. And I'll write that down because we know that now. We know that as long as when time equals 0 is at max pos, maximum positive displacement, A equals cosine omega t. X equals A cosine omega t. Well, velocity, we can sort of figure out what the graph would look like from our analysis. Of course, at that moment, we decided that its velocity was 0. So if I do the velocity in orange here, and well, a quarter of a cycle later, it's zooming through equilibrium at negative maximum velocity. So that's going to be right somewhere down here, isn't it? I mean, it's a different scale for velocity. So I've kind of done something like this. Then when we get halfway through the cycle, it says maximum negative displacement, and it's stopped again. It's come crunching to a halt, so it goes through the equilibrium again. And finally, or the velocity does, and finally when the displacement is at equilibrium, but moving to the right, well, the velocity is a maximum because it's shooting to the right with maximum velocity. So that's going to be up here. Well, let's do, and then it repeats, so it goes back to where it started. Well, let's draw that on a separate graph. And there's our velocity graph. And we can see the shape is a negative sign. But we can do a lot more because we can label our maximum minimum values. So we know that our maximum velocity is omega A. We know that our minimum velocity is going to be minus omega A. And we know that it's a minus sign. So we can actually write down the equation for that graph. We can say, velocity of this oscillator is given by, well, it's a minus sign, and the amplitude of that is omega A. And it has the same frequency and time period and angular velocity as the displacement does. So we can actually write that down. So pretty powerful, and pretty cool. We've figured out an equation for the velocity of a simple harmonic oscillator at any given time, assuming that the displacement is given by A cosine omega t. Well, last thing, let's just line those graphs up, because we know that the displacement is this cosine and the velocity is this minus sign. So then let me just write the equations again. So remember that the displacement of this particular oscillator that we're dealing with was A cosine omega t. And then we figured out just now that the velocity is minus omega A sine omega t. And really important to just see that, of course, velocity is the gradient of displacement time graph in mechanics. We know that from basic mechanics. Yeah? Distance over time is speed, displacement over time is velocity. So that means that the velocity graph should be the gradient of the displacement time graph. Well, it looks like we're good there, because if we look at the gradient of the displacement time graph, well, in the first position there, at time equals 0, the gradient is 0. And bang, there's our 0, the velocity is 0. Let's look a little bit later. At a quarter of a way through the cycle, the gradient is looking something like this. And it's pretty steep, and it's negative, so it's a maximum negative value. Bang, velocity, maximum negative value, and so on. So hopefully you can see that it's true indeed that the velocity graph that we've produced is the gradient of the displacement time graph. So that's pretty cool. Last one there, positive and large at 3/4 of the way through the cycle, the gradient, and sure enough the velocity is positive maximum value and large, and then back to 0 right at the end of the cycle, and then that's just going to repeat. If you're doing maths, you'll spot, or if you've done differentiating trigonometrical functions in maths, you'll spot that the velocity is indeed the differential of the displacement. But if you're not doing maths, don't worry about that. All you need to be able to do is figure out what graph it should be from physics principles. So there's a fact to just leave this section with. The velocity of a simple harmonic oscillator is the gradient of the displacement time graph. So to find velocity, we can do one of two things. We can use the equation, or we could even draw a tangent ourselves. And questions do get you to do this. Draw a tangent at a particular point, often the maximum value, and you can find the gradient at that point to give you the velocity.